Good morning, everyone. Today, we're going to solve an application of the second-order differential equation. So, we're tasked to find the natural frequency of this system. The following equations are needed to solve the problem. This is the equation for the natural frequency of the system. And this equation is used to obtain the differential equation of the total energy of the system. So, PE, or the potential energy, is divided into two parts, PEA and PEB. Potential energy A is the potential energy of the weight. So, since as you can see, when the spring is stretched, the weight moves downward. That's why it is -2. And as the weight moves downward, the potential energy decreases. Then for PEB is the potential energy stored in the spring. So, delta is the equilibrium elongation of the spring, and delta plus y is the elongation, instantaneous elongation of the spring. So, the force of the spring is just equal to Ks ds from delta plus y. And integrating this, we will get So, our potential energy B is equal to K, which is the spring constant, times delta y plus 1/2 ky squared. Next, the kinetic energy. Also, the kinetic energy is divided into two parts, kinetic energy A and kinetic energy B. kinetic energy A is the energy of translation of the wave. So it is since our weight is 2W, so we have the kinetic energy A equal to weight over G, which is the gravitational constant, and y prime squared. So for KEB is the energy of rotation of the pulley. So as you can see, when the spring stretches, the cable moves and it gives a rotational, a sort of rotation to the pulley. So that is the KEB. It is defined as the 1/2 I, where I is equal to omega per 2G r squared, and so simplifying this, so this is now our KEB. Now, substituting these values of potential energy and kinetic energy to our total energy of the system equation, we have so now, this is our total energy of this system equation. So, deriving this, we will get the equation of motion. So, then we're going to divide both sides by 1 over y prime to get the differential equation. So we have So this is now our differential equation. Simplifying this, so this constant here is just our natural frequency. So now, the natural frequency of the system is equal to